There is a kind of danger in the universe that waits for you to make a mistake. A black hole is like that. It is patient. It is silent. It can tear stars apart, bend light into rings, and hide an entire region of space-time behind a horizon no signal can cross. But it does not hunt. It does not reach for you across the galaxy. If you keep your distance, a black hole is mostly just gravity in the dark. A magnetar is different. A magnetar is also a corpse of a star, but it is not remembered because of gravity. It is remembered because of magnetism so extreme that the word magnetic almost becomes useless. Its field can be 1,000 trillion times stronger than the field around Earth. Near its surface, atoms are not atoms in the way chemistry teaches them. Empty space itself behaves differently. Light changes its polarization, as if the vacuum had become a crystal. The crust of the star can crack under magnetic stress, and when it does, the released radiation can cross tens of thousands of light years and still disturb the upper atmosphere of a planet. That is the uncomfortable thesis of this journey. Black holes may be the deeper abyss, but magnetars are the more aggressive threat. Not because they are more massive, not because they last longer, not because they win every comparison. They do not. A black hole is more absolute at close range. A quasar can outshine galaxies for ages. But if terror means reach, surprise, and the ability to harm without being approached, then a magnetar deserves a darker place in the imagination. It is not a trap in space. It is a loaded fault line in a dead star. And when the fault line slips, the bullet is light. To understand why this matters, you have to begin where a magnetar begins, not in quiet, but in collapse. A massive star spends its life balancing two enormous forces. Gravity pulls inward, trying to crush the star into itself. Nuclear fusion pushes outward, turning light elements into heavier ones and releasing energy in the process. For millions of years, the star holds that balance. It burns hydrogen into helium, then helium into carbon and oxygen, then still heavier elements, each stage shorter and more frantic than the last. The star is not a campfire. It is a pressure vessel, and the pressure is bought with nuclear fuel. The final fuel is not really fuel at all. In the core of a massive star, silicon can fuse into iron, but iron is a wall. Fusion of lighter elements releases energy. Fusion of iron costs energy. When an iron core forms, the star can no longer pay the debt of gravity. There is no new fire strong enough to hold the center up. In less than a second, the core collapses. Matter that once occupied a volume comparable to a planet is driven into a sphere only about the size of a city. Protons and electrons are forced together into neutrons. Neutrinos flood outward. The outer layers crash down, rebound, and the star tears itself apart as a supernova. What remains depends on how much mass survives in the collapsed core. If the remnant is too heavy, no known pressure can stop the fall, and a black hole forms. But if the remnant lands in a narrower range, gravity is halted by quantum mechanics. Neutrons cannot all occupy the same state. Their degeneracy pressure holds the remnant up, not gently, but enough. The result is a neutron star, more mass than the Sun compressed into a sphere roughly 20 to 25 kilometers across. A teaspoon of neutron star matter would weigh billions of tons. Its gravity is so intense that light from the far side can curve around toward you. Its surface is not a place. It is a boundary between ordinary thinking and nuclear matter. Most neutron stars are already extreme beyond ordinary imagination. Many are born spinning rapidly. Some emit beams of radiation from their magnetic poles, and when those beams sweep past Earth, we see pulses with the precision of clocks. These pulsars taught astronomers that dead stars could be more regular than human-made timekeepers. Yet a magnetar is not merely a fast pulsar with a stronger field. It is a neutron star whose main source of visible violence is not rotation, but magnetic decay. The magnetic field itself is the energy reservoir. The star is powered by its own stressed magnetism. That difference matters. A normal pulsar spends rotational energy. It slows down as its beam carries energy away. A magnetar spends magnetic energy. Its field threads the crust and interior. It twists, decays, shifts, and forces the star's solid crust to bear stresses no material on Earth could survive. When the crust gives, the field rearranges. A sudden release follows. That is why magnetars produce bursts and flares rather than simply ticking like clocks. They are not merely rotating, they are breaking. The standard idea for how such a field is born is fierce, but not settled. In the classic picture, first proposed by Robert Duncan and Christopher Thompson, a newborn neutron star spins extremely fast, perhaps with a period measured in milliseconds. Its interior is hot, turbulent, and electrically conducting. Convection and rotation drive a dynamo, amplifying an initial magnetic field into the enormous fields observed in magnetars. That model remains powerful because it connects the violence of birth to the later violence of the star. But it is not the only path under discussion. Some magnetars may form through unusual supernova, mergers, or accretion-induced collapse. Recent observations have made the birth story less tidy, not more. The magnetar is not just an object of extreme physics. It is also a clue that our map of stellar death is incomplete. Here, the first counter-argument needs to be taken seriously. If magnetars are rare, short-lived, and often distant, why call them more terrifying than black holes? Black holes can last for inconceivable times. They can swallow stars. Supermassive black holes can power quasars, whose jets reshape galaxies. No magnetar can compete with that total scale. If terror means the most permanent gravitational abyss, the black hole remains unmatched. This argument is not weak. It is correct in its domain. But the domain matters. A black hole's most famous danger is local. Outside its immediate gravitational neighborhood, it behaves like any object of the same mass. Replace the Sun with a black hole of exactly one solar mass, and Earth would continue orbiting as before, though it would freeze without sunlight. The black hole does not suck in the galaxy. It bends space-time according to mass. Its event horizon is absolute if you cross it, but it does not chase you. A magnetar flare, by contrast, is a radiative event. It moves outward at the speed of light. If you are in the path and close enough, you do not have to approach the magnetar. The magnetar comes to you. To feel the difference, climb the ladder of magnetic fields slowly. Earth's magnetic field is weak, roughly a fraction of a Gauss at the surface. It is enough to turn a compass needle and to shape a protective magnetosphere, but you do not feel it in your bones. A refrigerator magnet may be tens or hundreds of Gauss at its surface. You can feel it snap to metal, but it is domestic, almost comic. A hospital MRI reaches tens of thousands of Gauss. At that point, metal objects become dangerous projectiles, and implants must be treated with care. Laboratory fields can climb still higher into regimes where even water and biological material respond measurably. Then, the human ladder ends. Neutron stars begin far above the human ladder. A normal neutron star can have a magnetic field around 1 trillion Gauss. That is already strong enough to distort the structure of atoms. Electrons that would ordinarily occupy familiar orbitals are forced into different patterns by the field. Chemistry becomes strange. The atom is no longer the small spherical system imagined in basic diagrams. It becomes squeezed and elongated, its possible states narrowed by a magnetic environment no laboratory can reproduce. A magnetar pushes this further, to fields around 10 to the 14th or 10 to the 15th Gauss. These numbers are not decorative. They are physics-crossing thresholds. In such fields, electrons are constrained into quantized motions perpendicular to the magnetic field. Matter near the surface may form exotic, elongated structures aligned with field lines. The ordinary language of molecules begins to fail because the electron arrangements that make ordinary chemistry possible have been rewritten by magnetism. A magnetar is not simply a neutron star with a bigger magnet. It is a place where the rules of matter have been forced into a different shape. And then the vacuum itself enters the story. In everyday thought, vacuum means nothing. In quantum field theory, vacuum is not an empty absence, but the lowest state of fields. It can respond to extreme conditions. Quantum electrodynamics predicts that in magnetic fields far beyond anything on Earth, the vacuum should become birefringent. Light polarized in one direction travels differently from light polarized in another, as if empty space had acquired the optical properties of a crystal. This is not mystical. It is a consequence of how electromagnetic fields interact with virtual charged particle pairs in QED. Observations of strongly magnetized neutron stars have offered evidence consistent with this effect, though researchers continue to refine the interpretation. The caution matters. It would be easy to say that a magnetar tears particles out of nothing, or that it turns the vacuum into matter like a magician opening a hidden door. The real story is subtler. There is a critical quantum field strength associated with electron behavior, and magnetars can exceed it. Under the right conditions, especially with high-energy photons and curved field geometry, processes such as photon splitting and pair creation become important. But a static magnetic field alone is not a cartoon machine that endlessly manufactures matter from empty space. The truth is more rigorous and more interesting. Near a magnetar, the vacuum is not passive. It participates. That participation is what makes the object feel almost hostile. In human life, magnetic fields are tools. They lift objects, store data, steer particles, scan bodies. Around a magnetar, the magnetic field is not a tool. It is the environment. It is stronger than the crust. It dominates plasma. It controls radiation. It reshapes matter and modifies the behavior of light. The field is not a feature of the star. The star is almost a container for the field's violence. The energy stored in such a field is enormous. Magnetic energy scales with the square of field strength. Increase the field by a factor of 1,000, and the stored energy can rise by a factor of 1,000,000, depending on volume and geometry. Magnetars store enough magnetic energy to power bursts that would be impossible for ordinary rotation alone to explain. Their radiation is not drawn primarily from the steady burning of a star. It comes from a wound in magnetic structure. That wound forms because the star is solid in a way that also strains imagination. A neutron star has a crust, not rock, but a lattice of nuclei and electrons under extreme pressure. It is likely among the strongest solids in the universe, yet even this crust can fail. Magnetic fields thread through it and through the interior. As the field evolves, it pushes sideways, twists, and stresses the crust. For a long time, the crust resists. It stores strain. Then, suddenly, a region yields. A starquake begins. The word earthquake is too small, but the analogy helps. On Earth, stress accumulates along faults until rock breaks. Energy is released into seismic waves. Buildings shake because the ground moves beneath them. On a magnetar, the cracking crust can release magnetic energy orders of magnitude beyond anything a planet could produce. The star rings. The magnetosphere responds. Field lines rearrange. A burst of X-rays and gamma rays leaves the surface. In small events, the burst may last milliseconds. In giant flares, the star briefly becomes one of the brightest high-energy sources in the sky. There are levels to this violence. Magnetars can produce short bursts, brief flashes in X-rays or soft gamma rays. During active periods, some sources burst repeatedly, like a stressed structure settling through many small failures. There are larger outbursts lasting days to months as the crust and magnetosphere adjust. And then there are giant flares, the rare events that define the legend of magnetars. Only a few have been observed from galactic or nearby sources in the era of space-based high-energy astronomy. That rarity is important. Magnetars are not constantly sterilizing worlds. Most of the time they are quiet. But rare does not mean harmless. A rare bullet is still a bullet if it is fired in your direction. The most famous bullet arrived on December 27, 2004. The source was SGR 1806-20, a magnetar often placed tens of thousands of light-years away in the Milky Way. Distance estimates have varied, and that uncertainty matters because energy estimates depend on distance. But even with caution, the event was extraordinary. In about a fraction of a second, the flare released an immense burst of gamma rays and hard X-rays. Satellites designed to monitor high-energy radiation were saturated. Instruments across the solar system detected the flash. Earth's upper atmosphere responded. A dead star on the far side of the galaxy had reached the planet. This is where the central comparison becomes physically sharp. The magnetar did not pull Earth with gravity in any meaningful new way. It did not move us. It did not open a hole in space. It sent radiation. That radiation crossed the galaxy at light speed and arrived as the first and only warning of itself. If it had been much closer, the same type of event could have been dangerous to an atmosphere and, at still closer distances, to surface life. The exact hazard depends on distance, spectrum, beaming, atmospheric chemistry, and planetary shielding. But the principle is sound. High-energy astrophysical radiation can damage ozone chemistry and increase surface ultraviolet exposure. A close enough burst is not just an astronomical event, it is a biological event. That does not mean Earth is under immediate threat from a known magnetar. The nearest confirmed magnetars are not next door in stellar terms. They are thousands of light-years away, and no known active magnetar is close enough to be a present extinction-level danger. This is the second counterargument, and it deserves to be stated plainly. Popular fear often exaggerates magnetars by implying that one could kill us from anywhere in the galaxy. That is not true. Distance saves us. The inverse square law is a mercy. Radiation spreads out. A flare that disturbs satellites from tens of thousands of light-years away is not automatically a flare that kills from that distance. The galaxy is large, and most magnetars are far. But the fact that distance saves us is not the same as saying the object is tame. A black hole also becomes harmless at sufficient distance. A supernova also becomes harmless if far enough away. Astrophysical danger is always a question of range. What makes magnetars special is that their range, bem machine of over air der range, during major flares can be measured in light years to thousands of light years for meaningful atmospheric effects, not merely in the immediate neighborhood of the object. A stellar mass black hole without an accretion disk cannot touch a planet from those distances. A magnetar flare can at least leave fingerprints. Those fingerprints are not only atmospheric. The 2004 flare was followed by a pulsating tail, modulated by the magnetar's rotation. In the radiation tail, scientists detected patterns that were interpreted as oscillations of the neutron star, almost like seismic modes. The magnetar had not only flared, it had rung. In that ringing, astrophysicists saw a chance to probe the crust and interior of an object impossible to visit. The same event that made magnetars frightening also made them scientifically precious. Violence became data. That dual nature is one of the reasons the story works so well as a documentary subject. A magnetar is not just a monster. It is a laboratory. It tests quantum electrodynamics in fields beyond human engineering. It tests nuclear physics at densities beyond the atomic nucleus. It tests how solids fail when gravity, magnetism, and quantum pressure all operate in the same body. It may even help explain fast radio bursts, those millisecond radio flashes from deep space that release extraordinary energy in almost no time. One galactic magnetar has already shown that magnetars can produce radio bursts far more powerful than ordinary pulsar pulses. Not every fast radio burst is solved by that fact, but the door is open. The object becomes more interesting when you stop saying it is simply more terrifying than a black hole, and ask why that phrase feels true. Black holes frighten us because they represent finality. A horizon is a boundary after which return is impossible. They are mathematical cliffs. Magnetars frighten us because they represent exposure. They make the universe feel less safely distant. They remind us that empty space is not perfect insulation. High-energy light can cross it almost unchanged. An event in a dead star can arrive at an atmosphere before any civilization could prepare. In other words, a black hole is horrifying because it says, "Come too close and you disappear." A magnetar is horrifying because it says distance is not always consent. That line is the spine of the argument. Magnetars do not defeat black holes in every category. They do not have event horizons. They do not create singularities. They do not swallow time in the same way. Their active lives are short by cosmic standards, perhaps 10,000 years for the strongest magnetic behavior, though the remnant itself lasts much longer as a neutron star. They are rare. They fade. Many become quiet, cold, and difficult to detect. A black hole can persist into eras when stars are gone. If the contest is endurance, the black hole wins. If the contest is gravitational extremity, the black hole wins. But if the contest is sudden reach, the magnetar has a claim. Let us make the black hole side stronger before returning to magnetars. A black hole with an accretion disk can be violently luminous. Matter spiraling into it heats to millions of degrees. Magnetic fields can launch jets. Around supermassive black holes, those jets can extend across vast distances and deposit energy into galaxies. Active galactic nuclei can influence star formation, heat gas, and shape cosmic evolution. In these environments, black holes are not passive pits. They are engines. They can outshine all the stars in a galaxy and maintain that output for long periods. So why not simply say active black holes are worse? Because the question is not which object can become the largest engine under the right conditions. It is which dead stellar remnant, considered as a direct hazard, has the more unsettling threat profile. A black hole's danger usually depends on environment. It needs matter falling in to shine violently. A magnetar's power is internal. Its magnetic field is the fuel. It can be isolated and still burst. It does not need a companion star. It does not need a disk. The mine is built into the remnant. That internal power is why magnetars complicate our instinctive hierarchy. We often rank cosmic danger by mass. Bigger means worse. But magnetars teach another rule. Concentration, field strength, and release mechanism can matter more than total mass. A mountain contains more mass than a bullet. The bullet is the immediate threat. A black hole contains the more absolute gravitational statement. A magnetar can send a flare into your atmosphere, while the black hole at the same distance does nothing. Danger is not a single number. It is a relationship between energy, range, duration, and the vulnerability of what receives it. A biological planet is vulnerable in specific ways. It needs atmospheric stability. It needs an ozone layer or some equivalent shield. It needs DNA or another information-bearing chemistry that can survive background radiation. It needs a surface or ocean environment not constantly sterilized by high-energy events. A magnetar flare attacks those conditions indirectly. The gamma rays may not reach the surface in full strength if the atmosphere is thick, but the atmosphere becomes the battlefield. Molecules are ionized. Nitrogen and oxygen chemistry changes. Ozone can be depleted if the event is strong and close enough. More ultraviolet radiation from the planet's own star reaches the ground. The original flash may last seconds. The biological consequences can last years. This is why scientists have considered high-energy astrophysical events as possible contributors to mass extinctions. The late Ordovician extinction, roughly 440 to 445 million years ago, has been discussed in connection with a possible gamma-ray burst or similar ionizing event. The hypothesis is not proven. Glaciation, sea level change, and and Earth system feedbacks remain central. But atmospheric modeling shows that a sufficiently nearby burst of gamma radiation could deplete ozone and raise ultraviolet stress in ways that would be severe for surface and shallow water life. The magnetar version of the story is not that we know a magnetar killed ancient life. We do not. The defensible claim is narrower. The physical pathway from high-energy cosmic radiation to biospheric stress is real enough to study. That scientific caution is not a weakness. It makes the story stronger. A bad documentary says, a magnetar caused an extinction. A better one says, the same kind of physics that disturbed Earth's atmosphere in 2004, if scaled by distance and energy, could become a planetary hazard. And Earth history contains events for which high-energy radiation remains a debated candidate among other explanations. The first version is louder. The second is more dangerous because it is true enough to matter. Now imagine a world much closer than Earth is to any known magnetar. It orbits a quiet star. Its oceans are full of primitive life. Its atmosphere has slowly built a protective layer against ultraviolet radiation. For millions of years, evolution advances under a stable sky. Somewhere a few hundred or a few thousand light years away, a magnetar has been quiet for centuries. No eye sees it. No civilization maps it. Then its crust fails. The flare leaves at the speed of light. There is no messenger ahead of it because nothing outruns light. When the news arrives, it is not news. It is the event. A society on that planet, if one existed, would learn about the flare only as its instruments saturated. The sky might not show a visible sign. Gamma rays do not announce themselves to human senses. The atmosphere would glow in wavelengths eyes cannot see. Radio communication might behave strangely. Satellites might fail. Over months, ultraviolet exposure could rise. Food chains could weaken from the bottom. The world would not know whether to call it weather, plague, radiation accident, or divine punishment. Only later, if it survived and had the right astronomy, would it trace the wound back to a dead star that had erupted before anyone on the planet knew the star existed. This is why the phrase, "you would never see it coming," is not just drama. It is built into relativity. The flare and the information that the flare happened travel together. If you could receive a warning before the radiation arrived, the warning would have outrun light. The universe does not allow that. A magnetar flare is therefore the perfect ambush in physical law. It cannot be forecast from afar unless you already monitor the magnetar and understand the internal stresses, which we do not. Even then, prediction would be probabilistic. The crust of a neutron star is not a weather system we can watch with satellites in orbit around it. It is a hidden fracture network in nuclear matter thousands of light years away. But even this ambush has limits. A known magnetar far across the galaxy is not a monster under Earth's bed. The 2004 event did not kill us. It did not strip the atmosphere. It was a warning only in the scientific sense. It showed the scale of the phenomenon. The honest version of the threat is not magnetars can destroy Earth at any moment. The honest version is magnetars reveal a mode of cosmic violence that can reach far beyond the object's immediate neighborhood. And if such an object were much closer, the consequences would be severe. That distinction is where science remains science instead of becoming fear marketing. The close-range physics is even stranger than the long-range hazard. Near a black hole, your body dies by gravity. Tidal forces stretch it, pull harder on one part than another, and eventually reduce structure to a stream of matter. Near a magnetar, your body dies earlier and differently. Long before you touch the surface, radiation and magnetic fields would make biology impossible. Strong magnetic gradients could exert forces on diamagnetic materials like water. More importantly, the field strength near the star would distort electron orbitals and chemical bonds. The molecules that make cells possible would not remain themselves. You would not be crushed in the ordinary sense. You would be chemically disassembled by a field that rewrites the conditions under which matter can be organized. This layered hostility is rare. A magnetar has gravity. Though less extreme than a black hole's horizon, it has radiation, sometimes in violent bursts. It has magnetism capable of altering atomic structure. It has a magnetosphere, filled with high-energy particles. It has a crust under stress. A black hole's identity is deeper and cleaner. Geometry, horizon, no return. A magnetar's identity is messier. Field, crack, flare, burst, atmosphere, chemistry. It is not one terror. It is several stacked together. The first time astronomers recognized something like this class of object, they did not immediately call it a magnetar. The story passed through soft gamma repeaters and anomalous X-ray pulsars, two names that sound technical because they were born from symptoms. Some objects emitted repeated bursts of soft gamma rays. Others emitted too much X-ray power to be explained by their rotation alone. Over time, timing measurements showed that these objects were neutron stars spinning slowly and slowing down rapidly implying enormous magnetic fields. The theoretical magnetar idea gave the symptoms a common cause: magnetic decay. That history matters because it shows how science actually moves. Magnetars were not invented because someone wanted a scarier black hole. They emerged because several odd astronomical behaviors needed a power source. Repeating gamma bursts, persistent X-ray emission, spin-down rates, and later giant flares all pointed toward a neutron star where magnetism was not secondary, but central. The object became terrifying after the data, not before it. The number of known magnetars has changed with time and will keep changing. Catalogs list around a few dozen confirmed and candidate sources, depending on classification. New objects appear when a previously quiet source erupts. Some magnetars act like radio pulsars for a time. Some seem to switch states. Some may be linked to fast radio bursts. The family is small, but it is not static. The galaxy may contain many dormant or older magnetars too faint to identify as magnetars today. That does not mean hidden death stars surround us. It means the census is incomplete, especially for quiet, compact remnants. This uncertainty cuts both ways. It makes sensational claims weaker, because we cannot point to a nearby unknown magnetar and say it will flare. But it also makes the subject scientifically alive. The most dangerous unknown is not necessarily a secret object near Earth. It is the unknown physics of neutron star interiors. How does the magnetic field evolve? How does the crust break? How does the core couple to the surface? How much energy can a flare release? Are the largest flares narrowly beamed or broadly emitted? How often do giant flares occur in a magnetar's active life? Each answer changes the hazard calculation. Inside the star, the physics becomes a negotiation between phases of matter no human experiment can fully reproduce. The crust is crystalline, but not like crystal on Earth. The outer layers contain nuclei and electrons. Deeper down, neutrons drip out of nuclei. Farther in, matter may become a superfluid. Protons may be superconducting. The core could contain exotic particles or phases we have not confirmed. Magnetic flux may be anchored in some regions and move through others. The field outside is what we infer, but the field inside may be stronger, twisted, and hidden. The flare is the surface language of a deeper structure we are only beginning to translate. This is why a magnetar is not simply a known weapon with unknown distance. It is also an unknown engine with known symptoms. The 2004 giant flare tells us what the engine can do at least once. The smaller bursts tell us it releases energy in a range of scales. Observations of changing pulse profiles tell us hotspots form and decay. Quasi-periodic oscillations hint at vibrations in the star, but the exact internal map remains disputed. Magnetars are not solved. They are a frontier in dense matter physics disguised as astronomy. The comparison with black holes becomes more subtle here too. Black holes are mathematically simpler in some ways. Once you know mass, charge, and spin, a classical black hole is described by a small set of parameters. Astrophysical black holes become complex because of their environments. Disks, jets, magnetic fields, companions. The black hole itself is almost austere. A magnetar is the opposite. It is a physical object with a surface, crust, field, interior, atmosphere, magnetosphere, thermal history, and fracture behavior. It is not a clean hole in geometry. It is a machine made of extreme matter, and machines can fail in complicated ways. That failure is the source of the documentary tension. A black hole is frightening because it is inevitable once crossed. A magnetar is frightening because it is conditional before it fires. The crust has not cracked yet. The field has not snapped yet. The flare has not happened yet. Everything is quiet. Then the condition changes. The event moves outward at light speed. A black hole is the terror of crossing a boundary. A magnetar is the terror of not knowing a boundary exists until it passes through you. To give the fear a human scale, consider Earth itself. Our planet's magnetic field protects us from charged particles, especially from the solar wind. The atmosphere protects us from most high-energy photons. The ozone layer protects surface life from much of the sun's ultraviolet radiation. These shields are not invincible. They are tuned to the ordinary environment of our star and galaxy. A strong enough ionizing event from space can stress them. The sky does not have to fall. It only has to alter chemistry in a thin region of the atmosphere for consequences to move through ecosystems. Life often depends on thin margins. DNA can repair damage, but not unlimited damage. Plankton can reproduce quickly, but not if ultraviolet exposure exceeds their resilience at the wrong time and depth. Agriculture can survive weather, but not years of disrupted atmospheric chemistry and radiation stress without cost. Technology can harden satellites, but not every system is shielded against extreme high-energy events. A magnetar flare from a safe distance is a scientific spectacle. From a dangerous distance, it becomes a test of every fragile layer between space and biology. Fortunately, Earth is not known to sit in that dangerous zone. This point should be repeated because fear without scale is dishonest. The Milky Way is huge. Known magnetars are far. Giant flares are rare. The probability that an active nearby magnetar will produce an extinction-level flare in the near future is extremely low based on current knowledge. The account of this story is not a warning to panic. It is a correction of imagination. We have been trained to place black holes at the top of cosmic fear. Magnetars show that the universe has other categories of danger, not swallowing, but irradiation, not gravity, but field, not proximity, but reach. The reach is visible in the way magnetars may masquerade as other phenomena. A giant flare in a nearby galaxy can look to detectors like a short gamma-ray burst. For years, short gamma-ray bursts were primarily associated with neutron star mergers, and many are. The merger model gained dramatic support when gravitational waves and electromagnetic light were observed from a neutron star merger in 2017. But not every short burst must come from a merger. Some events in nearby galaxies appear consistent with magnetar giant flares. A single cracked crust can imitate the death spiral of two compact stars. That is not merely frightening, it is humbling. The universe can produce similar signals from very different engines. Fast radio bursts deepen the puzzle. These millisecond radio flashes are observed across cosmological distances. Their origins may not all be the same. Some repeat, some do not. Magnetars are one compelling source class because a galactic magnetar has produced an FRB-like radio burst along with high-energy activity. But here caution again matters. Magnetars are likely part of the FRB story, not necessarily the whole story. The source population may be mixed. The physics may involve magnetospheric reconnection, shocks, or other mechanisms. A good account does not say magnetars solve fast radio bursts. It says magnetars force the door open. They also force open a philosophical door about scale. A magnetar is small by astronomical standards. It is city-sized, yet its effects can be galactic. This violates a common intuition. Large effects should require large objects. But physics does not obey that intuition. What matters is energy density, field strength, and coupling. A neutron star contains solar mass in a city. A magnetar stores magnetic energy in a field anchored to that city. When released, the signal is not limited by the star's diameter. Light does not care how small the source was once it begins crossing space. That is why the opening image should stay with you. A dead star no larger than a city, hidden in the galaxy, quietly twisting its magnetic field. There is no expanding shell visible to your eyes, no villain shape, no cosmic mouth, just a point, perhaps invisible, perhaps faint in X-rays, with a crust under stress. The danger is not in what it looks like. The danger is in what it can suddenly become. Now consider black holes again, because the strongest version of the opposing view says this: black holes are not passive if they are feeding, and their jets can also reach across enormous distances. Relativistic jets from supermassive black holes can drill through intergalactic space, radiate across the spectrum, and shape entire galaxy clusters. If a civilization were near an active galactic nucleus, the black hole environment would be vastly more dangerous than any magnetar. This is true. The magnetar claim cannot be universal. It must be specific. The specific claim is about stellar remnants as threats to life at distance without approach. A stellar mass black hole by itself is safe at a few light-years. A magnetar at the same distance, if active and if it produces a giant flare, is not. A supermassive black hole in an active phase is a different category, a galactic engine with an accretion flow. It is not the quiet black hole of popular fear. When we compare the popular black hole to the magnetar, we are comparing the event horizon myth with the flare reality. The magnetar wins only in the arena of sudden projected hostility. That careful framing is what makes the argument debatable, rather than merely sensational. Someone can disagree by choosing a different definition of terrifying. They can say permanence matters more than reach. They can say the event horizon is conceptually more horrifying than a flare. They can say active black holes and quasars overwhelm magnetars in total output. They are not wrong. But the counterclaim remains. A magnetar can threaten from a distance while being almost invisible before the event, and that makes it uniquely disturbing for living worlds. The biology of fear responds to agency, even when there is none. We fear things that strike without warning because our nervous system evolved to handle predators, storms, and accidents. A black hole fits the fear of falling. A magnetar fits the fear of being hit. Neither object has intent. A magnetar does not attack. It does not choose. It is not angry. Its crust cracks because stress exceeds strength. Radiation follows because fields and particles obey physical law. The language of attack is useful for emotion but dangerous for science. The star is not hostile in mind. It is hostile in consequence. This distinction matters because the universe is not morally arranged. A flare that harms a planet is not punishment. A black hole that swallows a star is not evil. The danger comes from compatibility or incompatibility with life. Life is a narrow chemical pattern that flourishes in a narrow range of conditions. Magnetars are extreme conditions in compact form. They remind us that the universe does not need malice to be lethal. Physics is enough. The surface of a magnetar is itself a warning against assuming that ordinary categories survive. If one could stand above it, which no body could, the view would be warped by gravity and magnetism together. Light from background stars would bend. Polarization would be altered by the magnetized vacuum. X-rays would dominate. The visible star might be dim, but the invisible fields would be overwhelming. Beauty and danger would occupy the same space. This is often true in astrophysics. The most elegant structures are not the safest ones. Spiral galaxies, supernova remnants, accretion disks, aurora, all are beautiful because charged particles, radiation, gravity, and shock waves are doing violent work. The magnetar is the most compressed version of that truth. It takes the aftermath of a supernova and stores a new catastrophe inside it. The original star has already died. Its outer layers have already been thrown into space. Its core has already collapsed. One would think the story is over. But the remnant continues. It cools. It spins down. Its field decays. Its crust strains. The dead star is still capable of surprise. That continued activity changes the meaning of dead. A neutron star is a stellar corpse, but not a quiet one. A white dwarf cools slowly unless fed by a companion. A black hole waits unless matter falls in. A magnetar, while active, has internal unrest. Its death is not a period. It is an aftershock lasting thousands of years. In a human body, death ends metabolism. In a star, death can reveal new physics. A magnetar is a corpse, whose nervous system is magnetism. The metaphor is strong, but it must remain a metaphor. The magnetar does not think. It has no nerves, no will, no intention. Calling its field a nervous system would be poetry, not science. Yet poetry can help when the facts exceed intuition. The field threads the star, carries stress, releases energy, and sends signals into space. It is the structure through which the object changes. If the metaphor helps you feel the physics, keep it. If it makes you believe the star is alive, let it go. The real physics is already strange enough. A field stronger than any human-made field by many orders of magnitude. Matter compressed beyond atomic density. A crust stronger than steel by factors so large the comparison becomes comic. Bursts lasting milliseconds that release the energy of years of sunlight. Giant flares detectable across galaxies. Vacuum behaving like an optical material. This does not need exaggeration. The measured universe is more frightening than the invented one. One of the best examples of that measured strangeness is spin down. Magnetars often rotate slowly compared to young ordinary pulsars, with periods of seconds rather than milliseconds. At first, this seems to weaken the story. If they are born fast, why are they slow when observed? The answer is that their magnetic fields act as powerful brakes. A rotating magnetic dipole loses energy. In a magnetar, the field is so strong that rotational energy can be drained rapidly on astronomical timescales. The star that may have spun hundreds or 1,000 times per second at birth can later turn once every several seconds. Its slowness is not weakness. It is evidence of magnetic dominance. This also gives astronomers a way to estimate magnetic fields. By measuring the rotation period and how quickly the period increases, they infer how much magnetic braking is occurring. These estimates are model-dependent, and local fields can be more complex than a simple dipole. But the method provides the basic evidence. Magnetars are not ordinary neutron stars with ordinary fields. Their magnetic braking is extreme enough to place them in a separate class. Another clue is luminosity. Some magnetars emit more X-ray power than can be supplied by their loss of rotational energy. That mismatch was historically important. If spin-down energy is insufficient, another reservoir must be powering the emission. Magnetic decay provides that reservoir. Again, the claim is not just that magnetars have big fields, because big fields sound dramatic. The claim is that their observed behavior requires an energy source beyond ordinary rotation, and magnetic energy explains the pattern. The physical story therefore has a clear spine. A magnetar can be more frightening than a black hole when the question is not total gravity, but sudden projected hazard. The reason is not mystery or intention. It is stored magnetic energy in a compact neutron star, released when crust failure and magnetospheric rearrangement turn stress into X-rays and gamma rays. We have seen the fingerprints, repeated bursts, giant flares, saturated satellites, ionospheric disturbances, and magnetar-like flashes from active sources. The limitation is just as important. Magnetars are rare, their most violent youth is brief, known sources are far from Earth, and they do not surpass black holes in gravity or longevity. But the consequence remains. Our ranking of cosmic danger should include not only gravitational traps, but radiative weapons built by magnetic stress. That chain is the editorial stance of this film. It does not need to pretend magnetars are secretly worse in every way. It only needs to argue that popular imagination has over-indexed on one kind of terror and neglected another. Black holes are famous because their concept is simple. A place where escape is impossible. Magnetars are less famous because their horror requires more steps. Neutron star, magnetic field, QED, crust stress, gamma flare, atmosphere chemistry. But complexity should not make a danger invisible. Sometimes the harder monster to explain is the more dangerous one. The 2004 flare remains the central scene because it turns abstraction into contact. Before that event, one could still imagine magnetars as exotic but remote. After it, the distance between theory and Earth narrowed. The flare did not harm people, but it entered the technological body of civilization. It hit detectors, satellites, radio propagation, upper atmosphere measurements. The planet noticed, not emotionally, but physically. A thing 50,000 light-years away had left a trace on instruments orbiting a small, rocky world around an ordinary star. There is a humbling reversal in that. We often think of astronomy as passive observation. We look outward. We collect photons. We interpret signals. The universe is the object, and we are the observers. But a magnetar flare reminds us that observation can be imposed from outside. The universe also sends events to us. Sometimes a source does not wait to be studied. It floods the detectors and forces itself into the data. The astronomer does not point the telescope at the magnetar. The magnetar lights up every high-energy instrument it can reach. This is why magnetars are valuable beyond their danger. They are unplanned experiments. No laboratory can create a neutron star. No laboratory can build a quadrillion Gauss magnet. No laboratory can fracture a crust of nuclear matter and watch the response. Magnetars run those experiments for us in the sky. They do so rarely and unpredictably, which is inconvenient. But when they do, they reveal physics otherwise sealed away. A giant flare is both a threat model and a research opportunity. It is a disaster that happens safely far away enough to become knowledge. Knowledge, however, should not erase awe. A common mistake in science communication is to treat explanation as deflation. Once you know that lightning is electrical discharge, it is no longer mysterious. Once you know that aurorae are charged particles guided by magnetic fields, they are less magical. But the reverse should happen. Understanding should make the event larger, not smaller. A magnetar is not less terrifying because we can explain its field as a neutron star dynamo, and its flares as crust failures. It is more terrifying because the explanation works. It means the monster is not a myth. It has equations. The equations also reveal how small Earth is in the face of high-energy astronomy. Our atmosphere is thick enough for us, but thin compared with cosmic violence. Our magnetosphere is large compared with Earth, but small compared with the distances light crosses effortlessly. Our technology is sophisticated compared with stone tools, but fragile compared with gamma-ray fluxes that saturate satellites. A civilization can be advanced and still be a surface phenomenon protected by gas. Magnetars remind us that habitability is not only about the warmth of a star and the presence of water, it is also about the history of nearby catastrophes. This matters for exoplanets. When astronomers search for life, they often begin with habitable zones, where liquid water could exist on a planet's surface. But a planet can sit in the right temperature zone and still be repeatedly sterilized by astrophysical events. Dense star-forming regions, galactic centers, and environments rich in massive stars may face more supernovae and gamma-ray events. Magnetars are part of that larger hazard landscape. A planet's biological future depends not just on its orbit, but on its cosmic neighborhood. Where you live in a galaxy can matter. Again, magnetars are not the only hazard. Supernovae, long gamma-ray bursts, active galactic nuclei, cosmic rays, stellar superflares, and nearby compact object mergers all belong in the conversation. The argument is not to crown one object as universally deadliest. It is to correct a blind spot. Magnetars combine compactness, magnetic extremity, and sudden repeatable flaring in a way that makes them uniquely hostile at certain ranges. They are not the biggest catastrophe. They are the most surprising one to people who thought black holes had no rival. Imagine teaching cosmic danger as a map rather than a ranking. In one region of the map are black holes, close-range gravitational finality, accretion-powered radiation if fed, extreme longevity. In another region are supernovae, broad explosive death of massive stars, heavy element creation, radiation, and shock. In another are gamma-ray bursts, narrow or broad beams of enormous energy, usually from collapses or mergers. Then magnetars occupy their own region, compact magnetic remnants, rare giant flares, persistent high-energy activity, fields beyond quantum thresholds. Once seen this way, the universe is not a single monster. It is an ecosystem of hazards, each with its own mechanism. Mechanism is the key word. A sensational claim says magnetars attack. A scientific claim says magnetars release stored magnetic energy through crustal and magnetospheric processes, producing high-energy photons capable of atmospheric ionization at large distances. The first line is useful for a thumbnail. The second is why the thumbnail is allowed to exist. Without mechanism, fear is empty. With mechanism, fear becomes understanding. That understanding also protects against false extremes. A magnetar cannot disrupt the atoms in your body from halfway across the galaxy under ordinary conditions. A giant flare can affect Earth's atmosphere from across the galaxy, but lethal biological effects require much closer distances. A magnetar does not tear apart the structure of every matter system in its galaxy. Its magnetic field weakens with distance. Its radiation spreads. The most dramatic close-range effects are real in principle, but confined to the magnetar's neighborhood. Precision does not weaken the account. It prevents it from collapsing under fact-checking. So let the revised terror be exact. Near the surface, magnetism dominates matter. Farther out, radiation dominates hazard. Across the galaxy, a giant flare can still be measurable. At Earth today, known magnetars are not an emergency. That is the shape of the truth. It is not as simple as safe or doomed. It is a landscape of distance. Distance is what saved us in 2004. The flare was immense, but space diluted it. By the time it reached Earth, It was a scientific event, not a biological catastrophe. That fact should produce gratitude, not boredom. A universe in which the same event can be harmless at one distance and catastrophic at another is a universe where survival often depends on geometry. We were not protected because the event was weak. We were protected because we were far enough away. There is an eerie fairness in that. The universe does not single out Earth. It does not aim magnetar flares at us. It does not spare us either. We occupy a location. Events happen. Light travels. Atmospheres respond. The rest is distance, timing, and physics. Life is not outside the cosmic system, watching from a safe balcony. Life is embedded in it. Every biosphere is a local experiment inside a galaxy that has no obligation to remain calm. This is why the final image should not be panic, but humility. Somewhere in the Milky Way, magnetars exist. Some are known. Some may be quiet. Some have already spent their fury and faded. Some are still young enough for their fields to crack their crusts. Most will never matter to Earth. One may flare tonight and be too far away to do anything but add data to a detector. Another may flare in a nearby galaxy and be classified at first as a short burst. The universe is full of events that are both remote and real, and somewhere, perhaps on a planet we will never see, a magnetar may be close enough to matter. Its flare may arrive in a sky that has never known astronomy. It may change atmospheric chemistry, alter mutation rates, collapse food chains, or erase a biosphere before intelligence has a chance to ask why. That possibility should not be sold as certainty. It should be held as a reminder that cosmic habitability is a fragile arrangement, not a guaranteed gift. The black hole remains the greater symbol. It is the perfect metaphor for finality, for secrets, for the edge of knowledge. The magnetar is a rougher symbol. It is the reminder that the universe's dead things can still have afterlives. A collapsed core can keep breaking. A magnetic field can outlive the star that generated it. A flare can turn a remnant into a beacon bright enough to cross intergalactic space. Death in astrophysics is not always silence. Sometimes death rings, cracks, and flashes. The next time someone says black holes are the scariest objects in space, the right answer is not simply no. The right answer is, it depends what scares you. If you fear a boundary from which nothing returns, fear black holes. If you fear a wound in space-time, fear black holes. If you fear the long future of the universe, when black holes may be among the last remaining structures, fear black holes. But if you fear invisible violence arriving without warning, if you fear a dead star that can reach across light years without you ever moving toward it, if you fear a field strong enough to make matter and vacuum behave like alien substances, then fear magnetars. The argument ends there, but the sky does not. Tonight, above the atmosphere, the galaxy will look quiet. Most of its compact remnants will be invisible. Black holes will not announce themselves unless they feed. Neutron stars will sweep beams through darkness. Magnetars will wait in their brief, active youth, their fields decaying, their crusts bearing stress. Some will sleep. Some will crack in small bursts. And perhaps somewhere far away, one will release a giant flare that began its journey before human civilization existed and will arrive at some future detector as a spike of hard light. No sound will come with it. Space cannot carry the scream. There will be only photons, data, saturation, ionization, a signature rising too fast for warning. A dead star will have spoken in the only language it has, and the message will be older than history by the time it is heard. That is the real horror of magnetars. Not that they are evil, not that they are coming for us, not that they overthrow black holes in every cosmic category. The horror is cleaner and colder. They prove that the universe can build a weapon out of a corpse, load it with magnetic energy, hide it in the dark for thousands of years, and fire it across the galaxy at the speed of light. A black hole can be avoided if you know where it is. A magnetar flare, close enough and strong enough, is something you only learn about when it arrives. To deepen the comparison, it helps to return to the birth of the neutron star and slow the collapse down in the imagination, even though nature does not slow it down at all. In the final second of a massive star's life, the core loses its support so abruptly that ordinary words like falling or shrinking fail. The collapse is not the slow compression of a machine press. It is matter losing the rules that held it up. Electrons are driven into protons. Neutrinos, almost ghost-like under ordinary conditions, are produced in unimaginable numbers. A shock wave forms, stalls, is revived by neutrino heating and turbulence, and then the star's outer layers are thrown outward. The explosion is not neat. Modern simulations still wrestle with the details of how the shock is revived in different stars. Even the ordinary supernova that makes a neutron star is a frontier problem. That is important because a magnetar asks even more of the explosion. It requires not just a neutron star, but a neutron star with unusual magnetic inheritance or unusual early rotation. One model begins with a fast-spinning newborn remnant. Another emphasizes magnetic flux conservation, the idea that if a star already had a strong magnetic field, collapsing it into a much smaller volume could intensify the field enormously, like forcing the same number of field lines through a smaller surface. Other models invoke binary interaction, mergers, or the collapse of a white dwarf under special conditions. None of these possibilities should be treated as a settled universal pathway. The science is still moving. Magnetars are not only frightening after they form, they are also difficult to explain before they form. That uncertainty adds texture to the story. If every magnetar had the same clean origin, the object would be easier to categorize. Instead, the evidence suggests diversity. Some are associated with supernova remnants, as expected. Some seem displaced from obvious birth sites. Some are very young. Some are radio loud at times. Some produce bursts after long, quiet periods. The category magnetar may include several routes to the same broad condition. A neutron star whose magnetic field dominates its emission and evolution. Nature may have more than one way to make a magnetic monster. The magnetar's youth is also misleading. 10,000 years sounds brief, but a civilization can appear, build monuments, invent writing, transform a planet's surface, and enter the digital age in less time. A magnetar born at the dawn of agriculture could still be active today. On geological scales, it is a spark. On human scales, it is an age. This mismatch is part of the fear. A phenomenon can be cosmically brief and still last longer than recorded history. The universe does not need long-lived threats to matter to beings whose entire species' history is short. Now place that youth inside the scale of the galaxy. The Milky Way contains hundreds of billions of stars. Massive stars are rare, but they die quickly. And over billions of years, they have produced enormous numbers of neutron stars. Most are invisible to us. Some are pulsars. Some are in binaries. Some are cold and quiet. A fraction are magnetars during a short active phase. The few dozen known sources are not a census of all that exist or have existed. They are the loud ones, the recent ones, the ones whose signals reached our detectors in a form we could recognize. The galaxy is a graveyard where only some graves glow. That graveyard image is useful but incomplete. A neutron star is not a grave marker. It is the compressed center of a star that once forged elements. The calcium in bones, the oxygen in water, the silicon in rock, and the iron in blood all owe something to earlier stellar generations. Massive stars die violently, and their remnants can become neutron stars or black holes, but the matter they expel becomes planets and bodies. The same death that makes a magnetar can seed life elsewhere. This is the paradox of violent astrophysics. It destroys locally and creates chemically. A universe without massive star death might be calmer, but it would be poorer. It might not have the heavy elements needed for living worlds. So the magnetar is not an alien intrusion into a peaceful universe. It is a byproduct of the same cosmic recycling that made rocky planets possible. Its terror is born from the same process that made your atoms. That makes the story more intimate. We are not threatened by something outside the history of matter. We are made from the family of events that can also produce threats. The universe's creativity and violence are not separate departments. The magnetic field itself is a fossil of the star's collapse and early seconds, but it is also an active participant in time. Magnetic fields carry energy and stress. In neutron star matter, they can thread regions that conduct almost perfectly. They can be locked into the crust in some ways and evolve through the interior in others. Over thousands of years, the configuration changes. This evolution is not a smooth unwinding like a watch spring. It can be uneven, because the crust has strength. Stress can remain hidden until a threshold is crossed. That threshold behavior is what makes prediction hard. Earthquakes are difficult even on a planet covered with seismometers. We know plate boundaries, stress accumulation, and fault histories, yet exact prediction remains beyond us. Now imagine predicting starquakes in an object thousands of light years away, with no probes, no surface instruments, no direct view of the interior, and matter in phases not found on Earth. When a magnetar flares, it is not surprising that it was hard to predict. It would be surprising if we could predict it well. This limits the way any responsible documentary should use the word warning. There is no practical early warning system for a distant magnetar giant flare that could protect a planet in its path, but there is scientific monitoring. High-energy satellites can detect bursts. X-ray telescopes can track outbursts. Radio telescopes can follow possible afterglows. Timing observations can measure spin and spin down. Polarimetry can probe magnetic geometry. Each tool gives a partial view, a different shadow of the same hidden engine. We cannot forecast the crack, but we can learn the material from the sound it makes when it breaks. The 2004 flare, for example, did not merely blind instruments. Its afterglow in radio revealed an expanding nebula of material and magnetic energy. That afterglow helped astronomers estimate how much energy had been ejected in particles and fields, not just photons. The flare was not a single flash in a vacuum. It shook the environment around the magnetar. It created a transient structure that expanded and faded. In this way, the flare left footprints after the light had passed, giving scientists more than a spike on a detector. This is another difference from black holes in popular understanding. Black holes often conceal. Their central region is hidden by the event horizon. We study them through the behavior of matter outside, gravitational waves from mergers, or the shadow cast by hot plasma. Magnetars reveal their interiors by failing. Their bursts are surface and magnetosphere events, but their timing and oscillations can carry information about the crust and core. A black hole's horizon is a closed door. A magnetar's cracked crust is a door violently kicked open, if only for a moment. What does it mean for the crust to ring? In ordinary seismology, the Earth vibrates in modes after large earthquakes. Those modes tell geophysicists about the planet's interior. A neutron star can do something analogous. After a giant flare, fluctuations in the tail of emission can be interpreted as global or crustal oscillations. The exact models are debated because the star's magnetic field couples crust and core in complex ways. But the idea is powerful. The flare does not only threaten, it turns the neutron star into an instrument, and the universe briefly plays it. The strongest magnetic fields also raise questions about radiation transport. Photons near a magnetar do not simply stream outward as they would from a normal star. They move through a magnetosphere where electrons, positrons, and magnetic field geometry reshape their paths and spectra. Some photons may split into lower energy photons. Some may create pairs under the right conditions. Scattering changes depending on polarization and field direction. A magnetar flare is therefore not just a light bulb turning on. It is radiation fighting its way through a quantum electrodynamic storm. This is why words like X-ray and gamma ray do not fully communicate the danger. Visible light interacts mostly with surfaces and molecules in familiar ways. Gamma rays interact with atoms at a more violent level. They ionize. They penetrate. They produce secondary particles and chemical cascades. A magnetar flare is not dangerous because it is bright in the human sense. It is dangerous because its photons carry enough energy to change atoms and molecules as they pass. The sky can look normal, while the upper atmosphere is chemically transformed. That invisibility is psychologically important. Human fear is trained by senses. Fire glows, thunder sounds, predators move, floods rise. Gamma radiation from a magnetar is not presented to our senses as a wall. If a dangerous flare arrived, the first direct human experience might not be awe, but delayed biological consequence. Instruments would know first, then chemistry, then ecosystems. In a technological civilization, the initial story would belong to satellites, power systems, radio propagation, and atmospheric sensors, not to eyes. One might ask whether planetary magnetic fields help. They do against charged particles, but gamma rays are electrically neutral photons. A magnetosphere can deflect charged particles from the solar wind and cosmic rays, but it does not stop gamma rays in the same way. The atmosphere is the main shield against high-energy photons. That is why atmospheric thickness and composition matter. A planet like Mars, with a thin atmosphere and weak global magnetic field, would be differently exposed. A world with a dense atmosphere might absorb the radiation higher up, but suffer chemistry changes. There is no single answer for every planet. This planetary dependence makes magnetar hazard a problem for astrobiology, not merely astrophysics. A flare's biological consequence depends on the receiving world. Does it have an ozone layer? Is life underwater, underground, or on the surface? Does the biosphere rely on photosynthesis at shallow depths? Is the star already ultraviolet active? How rapidly can atmospheric chemistry recover? A magnetar does not simply deliver death. It delivers a stress that a planet translates through its own systems. The same flare could be a minor perturbation for one biosphere and a catastrophe for another. That is the real scientific advantage of avoiding absolute language. Absolute claims are easy to dramatize but brittle. Conditional claims are stronger. If a giant flare of a given energy occurs within a certain distance of a planet with a certain atmosphere, then ozone depletion and radiation stress may follow. This is not less interesting than magnetars can wipe out life. It is more interesting because it gives the public a mechanism they can test mentally. It turns fear into a physical chain. The chain also explains why magnetars matter even when far away. The 2004 event was not dangerous to surface life, but it was a calibration point. It showed that a magnetar giant flare could be energetic enough to be confused with short gamma-ray bursts in nearby galaxies. It showed that the energy release was not theoretical. It showed that Earth's atmosphere could respond measurably from a great distance. It gave scientists an empirical anchor for models. In risk science, rare real events are precious because they replace imagination with scale. Scale is the entire challenge. The magnetar is tiny by cosmic standards and yet immense in effect. It is short-lived in active phase and yet long enough to overlap civilizations. It is rare and yet numerous enough across galactic history to matter statistically. It is far and yet capable of contact. Every property resists a simple category. That resistance is what makes it a better subject than a list of scary facts. The story is not, magnetars are big. They are not. It is not, magnetars are common. They are not. It is, under the right conditions, an object small enough to fit within a city can release energy on a scale normally reserved for stars and galaxies. Consider the energy comparison carefully. Saying a flare releases as much energy as the sun emits over tens of thousands of years is emotionally effective, but it can mislead if not framed. The sun emits steadily in all directions over time. A flare releases high-energy radiation rapidly. The biological impact depends on fluence at the planet, not total energy alone. A flare far away can have less effect than a much smaller event nearby. Energy is not danger until geometry delivers it. This is why distance cannot be a footnote. It is part of the mechanism. The source direction also matters. Some magnetar emission may not be perfectly isotropic. If energy is beamed or structured, some directions receive more than others. For a planet, the difference between being in the beam and outside it could be enormous. This remains an area of uncertainty. The geometry of giant flares, trapped fireballs, magnetospheric reconnection, and outflows is complex. Good science should leave room for that uncertainty rather than forcing a clean sphere of destruction around the object. There is also uncertainty in how often giant flares occur. Observing 3 major events in a few decades gives a clue, but the sample is small. Magnetars are rare, active phases are brief, and detectors have limited history. A rate estimate built from so few events must carry wide error bars. This is another reason not to overstate the present danger. We know giant flares happen. We know they can be enormous. We do not know their full distribution with precision. The largest possible magnetar flare may be larger than any seen, or the observed events may already represent the upper practical range. The data are not yet deep enough to be arrogant. That humility strengthens the comparison with black holes. Black hole theory is mature in the domain of general relativity, but astrophysical black holes also carry uncertainties in accretion physics, jet launching, magnetic fields, and feedback. Magnetars are less mature in many details. In both cases, the unknowns are not excuses for fantasy. They are invitations to sharper observation. A documentary about extreme objects should make the public feel both the fear and the discipline. The terror is real, but it must pass through evidence. Evidence has a texture. It includes timing measurements, spectra, polarization, burst light curves, satellite saturation, ionospheric response, radio afterglow, and catalogs of known sources. It also includes failures, flares we did not predict, magnetars whose birthplaces do not fit simple expectations, bursts whose origin is ambiguous. Science advances not by pretending those failures are solved, but by making them visible. The magnetar is compelling because it is not a closed chapter. It is an active research problem. Now move from research back to the body. What would happen to matter near a magnetar is often described with phrases like atoms stretched into needles. This is broadly meaningful, but it requires care. At strong magnetic fields, electron motion perpendicular to the field is quantized, and atomic structure changes. The atom becomes elongated along field lines. Chemical bonding under such fields would not resemble normal terrestrial chemistry, but the precise structure depends on field strength, element, density, and environment. The point is not that every atom literally becomes a cartoon needle of one fixed shape. The point is that the assumptions behind ordinary matter fail. That failure is what makes magnetars philosophically eerie. Black holes show where gravity breaks our everyday understanding. Magnetars show where electromagnetism, the force responsible for chemistry, light, and touch, becomes alien. Gravity is distant in daily life, except as weight and falling. Electromagnetism is intimate. It shapes every chemical bond, every nerve impulse, every material surface. A magnetar weaponizes the intimate force. It does not merely pull on mass. It changes the conditions for matter to be matter in a familiar way. This is why the phrase "more terrifying than a black hole" can be defended emotionally. A black hole destroys location and escape. A magnetar threatens identity at the level of chemistry. Near it, the molecular basis of a body is not stable. At distance, the radiation basis of a biosphere is stressed. It reaches both inward and outward. It is not only a place you cannot leave, it is a field in which the rules that assembled you stop applying. Yet the object itself is not chaotic. It follows laws. The field geometry can be modeled. The bursts have spectra. The spin period can be measured. The decay tail can be analyzed. This combination of lawfulness and violence is one of the strange comforts of astrophysics. The universe is not safe, but it is intelligible. A magnetar can be terrifying and not supernatural. It can be unpredictable in timing, but lawful in behavior. That makes it more useful to contemplate than any invented monster. The contemplation also reveals how much of human cosmic fear is aesthetic. Black holes look terrifying in visualizations. Dark centers, glowing disks, bent light. Magnetars may not look dramatic in visible light at all. They are high-energy objects. Much of their violence is invisible to our eyes. If popular culture had evolved around X-ray detectors instead of cameras, magnetars might already be more famous. Our mythology follows our senses, and our senses are poorly tuned to the most dangerous parts of the spectrum. This sensory mismatch affects public understanding. A flare in gamma rays can be far more consequential than a bright visible star, but because we cannot see gamma rays, the event feels abstract. We rely on instruments to translate it. The instrument becomes the witness. In the 2004 flare, the witness was not a human eye, but a network of detectors that suddenly received more signal than they were designed to handle. The story of magnetars is therefore also the story of how modern astronomy expanded the senses of our species. Without gamma-ray satellites, magnetars would remain mostly hidden. That expansion is recent. The sky known to ancient astronomers was an optical sky. The sky known to modern astronomy is radio, infrared, optical, ultraviolet, X-ray, gamma-ray, neutrino, cosmic ray, and gravitational wave. Each new sense reveals new monsters. Pulsars were invisible until radio astronomy found them. Black hole accretion became vivid in X-rays. Magnetars emerged in high-energy bursts. The universe was not calm before we built these instruments. We were simply deaf to much of its violence. There is a narrative lesson in that. Do not mistake silence for safety. Before the right detector, a magnetar is quiet. Before a flare, it is quiet. Before a civilization understands atmospheric chemistry, a burst is just a mystery in the fossil record, or a disturbance in radio propagation. The dangerous universe, Demialis, does not always announce itself in the language available to the observers. Sometimes the language has to be invented first, and perhaps this is why magnetars are worth placing beside black holes rather than beneath them. Black holes teach us about horizons and gravity. Magnetars teach us about fields and suddenness. Black holes ask what happens when space-time curves beyond escape. Magnetars ask what happens when magnetism becomes stronger than matter's ordinary organization. Black holes lead to questions about information loss and singularities. Magnetars lead to questions about quantum electrodynamics, nuclear matter, crust failure, and transient hazards. Each object is a doorway into different physics. Fear is only the beginning of the lesson. If this were only about danger, the story would end with risk assessment. Known magnetars far away. Giant flares rare. Earth safe for now. But the deeper value is perspective. A small remnant can reshape the sky. A dead star can remain active. A magnetic field can store enough energy to make a city-sized object briefly outshine almost everything. The universe is not arranged according to human intuition about size, stillness, or death. Once a massive star collapses, the story can grow stranger, not simpler. This perspective reaches back into the origin of matter around us. Supernovae create or disperse the heavy elements that later become planets. Some of those supernovae leave neutron stars. Some neutron stars become magnetars. The same chain that enriches the galaxy with the ingredients for life also leaves behind high-energy remnants capable of threatening life. Creation and risk are bound together. You cannot have a chemically rich universe without violent stellar death. You cannot have the iron in blood without stars massive enough to die. And if you have those stars, you also have remnants. A calm universe might be barren. A violent universe can be fertile and dangerous. That may be the most honest cosmic lesson. We live in the aftermath of explosions. We are shielded by an atmosphere that was shaped by life and geology. We orbit in a relatively quiet galactic neighborhood. We exist because many dangerous things are not too close at the wrong time. Habitability is a temporary truce between local stability and cosmic violence. The magnetar is one of the signatures of that truce's fragility. It does not mean life is doomed. It means life is conditional. Every biosphere depends on a surrounding environment that can change from beyond its star. Astrobiology must therefore think beyond planets. It must think in neighborhoods, histories, and event rates. The question is not only whether a planet has water, it is whether the sky around it has allowed water-bearing life enough time to become complex. That thought reframes the search for extraterrestrial life. A planet could form in a habitable zone and remain sterile because its region of the galaxy is too violent. Another could recover from repeated events because life shelters in oceans. Another could develop underground or under ice, where gamma-ray after-effects matter less. The relationship between magnetars and life is therefore not simple annihilation. It is selection pressure at the scale of worlds. Some biospheres might be pruned. Others might endure. A flare could reset complexity without destroying microbial life. The fossil record of another planet, if we ever read one, might carry the scars of distant compact objects. We do not yet read such records. We barely read our own. The Ordovician gamma-ray hypothesis remains one interpretation among many, not a settled verdict, but its existence shows the breadth of modern science, astrophysics, atmospheric chemistry, paleontology, and evolutionary biology can meet at a single question. Did something in deep space change life in the ancient ocean? Even if the answer is no for that specific event, the question itself is powerful. It proves that the boundary between astronomy and biology is thinner than it once seemed. A magnetar also reminds us that technological civilization is not the same as cosmic control. We can detect a flare, model it, publish papers, build detectors, and perhaps harden infrastructure against solar events. But we cannot stop a magnetar flare. We cannot move a planet out of the beam. We cannot negotiate with a starquake. The knowledge is not power in the simple sense. It is awareness. Sometimes awareness is all a species can have. A black hole pulls that fabric toward a horizon. A magnetar threads it with a field. Both are reminders that human life happens in the mild middle of physics. We live where gravity is weak enough for bodies. Magnetism is weak enough for chemistry. Radiation is low enough for DNA. And time is slow enough for thought. Extreme objects show us the boundaries of that middle. They are not exceptions to the universe. They are the universe showing what else its laws permit. What does a magnetar permit? It permits a city-sized object heavier than the sun. It permits a magnetic field that modifies vacuum optics. It permits a crust of nuclear matter to store stress until failure. It permits flares whose radiation crosses the galaxy. It permits a dead star to become for a fraction of a second, brighter in gamma rays than anything else in our sky beyond the solar system. If those permissions do not terrify you, it may be because the words have grown too familiar, so strip the words away. Picture a star that has already exploded. Its outer layers are gone. The remnant is small enough to hide inside a city, but every cubic centimeter is a challenge to matter. Its field lines rise and loop and twist through space. There is no sound. There is no visible fire. For years, nothing dramatic happens. The star turns once every few seconds, and with each turn, the field drags on its rotation. Inside, stress migrates. In the crust, a lattice bears more than it should. Then, in a patch no larger than a region of a city, failure begins. The crack does not need to be large by planetary standards. On a neutron star, small motions release huge energy because the densities and fields are huge. Magnetic field lines rearrange. A fireball forms, trapped by magnetism, hotter than almost anything in the present universe. Radiation builds. The magnetic cage holds until it cannot. Then the cage opens. The flare leaves. At first it crosses the magnetar's own magnetosphere, where particles and fields scatter, split, and redirect radiation. Then it enters interstellar space. Dust does not stop it. Gas barely matters. For thousands of years, perhaps tens of thousands, it travels. Stars move, civilizations rise and fall, ice ages come and go, the photons continue. When they finally enter another star system, there is no slowing. They meet a planet's atmosphere, and the atmosphere becomes chemistry. Detectors spike. Electrons are stripped from molecules. The event is over almost as soon as it is known. That is not a black hole story. It has no horizon, no falling astronaut, no frozen clock at the edge of space-time. It is a story of transmission. Energy created in a stressed magnetic corpse becomes a message that crosses the galaxy and is delivered to matter that never asked to receive it. The terror is not being swallowed. The terror is being reached. This reach also forces us to rethink the word empty. The space between stars feels like protection because it is vast, but for photons, vastness is only travel time. Space does not wear down gamma rays the way air wears down sound. It spreads them, yes, but it does not stop them. A sufficiently energetic event can remain meaningful after crossing distances that dwarf human history. Interstellar space is empty enough to let violence travel cleanly. The void is therefore not a wall, it is a corridor. A black hole makes the corridor end. A magnetar sends something down it. By now the thesis should feel earned rather than shouted. Magnetars are not more terrifying because the internet needs a new monster. They are more terrifying in a precise sense because their danger is active, radiative, and long-range. They do not invalidate black holes. They occupy a different nightmare. The universe is large enough for both. That understanding can make the night sky feel different. The points of light are not just decorative. Some are massive stars that will die. Some are remnants. Some regions hide neutron stars too faint to see. Somewhere, fields stronger than any human magnet are decaying. Somewhere, a crust is under stress. Somewhere, a detector on another world, if such a world exists, may one day record a spike and wonder whether it has just witnessed a distant starquake. The sky is not only a map of where things are, it is a map of what things can do. When you look up, you cannot see magnetars with your eyes. That is part of their lesson. The most important realities are not always visible in the band of light biology gave us. Our eyes evolved under sunlight, not gamma-ray astronomy. They are tuned for survival on a planet, not truth across the spectrum. The magnetar belongs to the universe our instruments discovered after our bodies reached their limit. It is a monster outside the native range of human perception. Maybe that is why black holes became famous first. Their darkness is visually imaginable. A hole that traps light is a simple picture. Magnetism strong enough to polarize vacuum, crack nuclear crust, and flare in gamma rays is harder to picture. It demands a more abstract fear, but abstraction is not absence. The fact that a danger is difficult to visualize does not make it weaker. It may simply mean we needed better senses. Meaning is where the ending should land. Magnetars are not important because they might kill us tomorrow. They are important because they show how wrong our instinctive universe is. Matter is not always gentle. Vacuum is not always passive. Dead stars are not always quiet. Distance is not always safety. Small objects can have vast reach. A thing can be rare and still rewrite the hierarchy of fear. So when the popular imagination says black hole, hear the magnetar behind it. Hear the slower rotation of a neutron star being braked by a field no planet could endure. Hear the crust under strain. Hear the vacuum turning optically strange. Hear the silent flare crossing the galaxy. carrying both destruction and information. The sound is not real because space is silent, but the physics is real, and that is enough. A black hole is the place where paths end. A magnetar is the thing that sends the end outward. That is the difference. That is why the dead star with the invisible field may deserve to stand beside the darkness with the horizon. And that is why, somewhere in the quiet between the stars, a city-sized remnant slowly cracking in the dark can be more frightening than the most famous monster in the universe.